To fully understand the concept of electrical conductivity, we must first be aware of the fact that various metals conduct electricity in very different ways. For example, metals are good conductors. However, on the other hand, plastics do neither flow electricity and are otherwise known as insulators. The differences in conductivity relates to the atomic structure of materials, referring to the ease of movement of the atom's electrons within their respective crystal lattice. But before we discuss the movement of electrons in solids, we should appropriately address the atom. In an isolated atom, the electrons occupy a series of energy levels around the positive nucleus, namely the valence and conduction band. Now, the valence band can be thought of as the outer shell of the atom, in which electrons partly or completely fill, whilst the conduction band can be thought of as a level where electrons are free to move between other atoms. As such, in metals, electrons are delocalized and free to move through the crystal lattice of positive ions. Comparatively, semiconductors require external energy in the form of heat or light in order for their rigid covalent bonds to allow for the movement of valence electrons into the conduction band. The energy band model can be used to illustrate the difference between conductors, semiconductors, and insulators. In conductors, the valence and conduction bands overlap. This merger allows for the sharing of delocalized electrons between bands and the effective conductance of electricity with minimal electrical resistance due to the absence of an energy gap. With insulators, there is a very large energy gap between the valence and conduction bands. This is known as the forbidden energy gap. In order to conduct electricity, electrons in an insulator must gain enough energy to jump from their valence band positions over the forbidden energy gap and into the conduction band. Because this process requires a great deal of energy, insulators have a high electrical resistance. Furthermore, semiconductors have band gaps smaller than that of insulators, but bigger than that of conductors, hence they lie in between. At room temperature, semiconductors are initially insulators. However, when provided with enough thermal or light energy, they are able to transfer electrons into the conduction band and conduct electricity. As this process requires external energy, semiconductors have a moderate electrical resistance dependent on temperature. Due to the nature of conductors, semiconductors, and insulators, the distance of the valence and conduction bands in each, comparatively the amount of electrons that drift from atom to atom, is in descending order, from conductors, semiconductors, to insulators. Depending on temperature and humidity, conductors will allow many electrons to be passed between atoms, semiconductors will allow less, and insulators shall have no sharing of electrons. When an electron is excited into the conduction band, it leaves a vacancy in the valence band. This vacancy is known as a hole. The hole behaves like a positively charged particle and moves in the opposite direction to the electron. In reality, the other electrons in the valence band move to fill this hole, leaving another vacancy behind, resulting in the apparent motion of the hole. It is this motion of electrons and holes that contribute to an electric current. Intrinsic semiconductors are pure semiconductor crystals consisting of only one element which conduct electricity through electron-hole pair conduction and have moderate conductivity at room temperature. Extrinsic semiconductors are semiconductors that have impurities added to their structure in order to increase their conductivity by modifying their electrical properties. The process of doping a semiconductor involves replacing some of the atoms of group 4 elements with atoms from group 3 or group 5 elements to reduce the energy input required for the substance to become conductive. Doping a semiconductor can change the semiconductor's electrical properties by changing the number of holes present or the number of free electrons. Now, if a group 3 element is added, then because it has one less electron in its outer shell, the lattice structure will be missing an electron. In this way, a hole is produced, and this hole is capable of moving charge. Similarly, if a group 5 element is added, there will be an extra electron in the lattice structure which is free to move between atoms and carry charge. Extrinsic semiconductors can be further classified into two types, of P and N, depending on the types of substances added to the intrinsic semiconductor. A group 4 element will have 4 valence electrons with no excess electrons or holes. However, when doped, some free electrons or holes may be present. If a group 4 element is doped with a group 3 element such as boron, there will be one electron short of bonding, and therefore a positive hole is formed. This then produces a p-type semiconductor because there is a deficiency of electrons. If a group 4 element is doped with a group 5 element such as phosphorus, there will be one electron left out of the covalent bond. This then produces an n-type semiconductor because it has an excess negative charges. Both materials are capable of carrying charge, as the p-type semiconductor has positive holes to move the charge, whereas n-type semiconductors have negative charge carriers to do the same. Holes and electrons flow in opposite directions in the crystal structure to conduct electricity, but they both enable the passage of current through the lattice. Thermionic devices operate on the principle of thermionic emission, where an electron is emitted from a filament due to high temperature within an evacuated glass tube. However, solid-state devices are composed of solid materials and function due to doped semiconductors and the flow of electrons. Solid-state devices and thermionic devices operate with the same purpose. They can modify, amplify or switch electric signals. However, the following factors contributed to solid-state devices replacing thermionic devices. Cost. Thermionic devices are more costly to produce due to their large size. Solid-state devices are much cheaper to make and are more economical when needed in large quantities. Size. The relatively large size of thermionic devices limits their uses. Solid-state devices such as diodes and transistors are considerably smaller. The trend of miniaturization of electron devices means that tiny solid-state devices are much preferred. Durability. Thermionic devices are extremely fragile. Solid-state devices are quite tough and can withstand a reasonable amount of physical impact. Energy efficiency. Thermionic devices require very high voltages for their operation. In addition, a large amount of heat is dissipated, which is energy wasted. Solid-state devices, on the other hand, only dissipate a small amount of energy due to their operation and require less energy to operate. Operational speed. Thermionic devices require a warm-up time to become usable. Solid-state devices operate at a much faster rate than thermionic devices, as they will function as soon as they are switched on. Shortcomings in technology, such as the inefficient use of thermionic devices and the continuous miniaturization of technology, force scientists to develop modern technology, such as the transistor. The transistor operates on the basis of a p-n junction. A p-n junction consists of two joined pieces of an n-type and p-type semiconductor and acts as a diode. A typical transistor consists of two p-n junctions and in close proximity of a piece of either n or p-type semiconductor sandwiched between two pieces of the opposing type of semiconductor. These regions or layers are known as the emitter, base, and collector layers. That's all for this video. Thanks for watching.